I wish you had my imagination.
All right, today let's look at how to do a piercing analysis like this inside LSDYNA, mostly through adaptive remeshing. Um, I'm gonna do a problem in 2D plane strain. I'm gonna do a problem in axisymmetric version of the problem. I'm gonna release it over two different videos at the same time. Um, okay, so agenda. I'm gonna go over some basics about 2D analysis in Dyna, just to have an overview of the basic element choices. And I'm gonna review some adaptive meshing setup requirement for piercing analysis. It's a pretty interesting and simple technique, but we can use this to sort of take advantage of remeshing capabilities to essentially separate a single part into two different parts through remeshing. And that's a really unique way in which we can sort of do some kind of like a peel or some kind of like milling or some type of piercing analysis. And then I'm gonna recreating an example on top of a basic piercing analysis. I'm also gonna recreate an example from Dynamore, which is gonna be the second part of the video right here. Okay, the basic logic behind a 2D analysis in Dyna, the reason I'm doing this in 2D because the remeshing step is very expensive. Let alone being in on the student license, it would take me a long time to solve. Even with the 2D analysis, it took like over an hour to solve, right? So I want to do this in 2D. So in Dyna, there are basically three element formulation inside the section shell keyword. Alform 12 is the plane stress, Alform 13 is plane strain, and Alform 15 is going to be axisymmetric. 13 and 15 are the most commonly used 2D method that I will use to look at analysis in 2D in Dyna. There is also an Alform 14, which is area weighted. This is mostly more common to explicit analysis for like explosion type, not very commonly used in my opinion. And then of course lastly we have Alform 11, which is for a 2D ALE problem. This is more, like a simplified version of a traditional 3D ALE elements that we'll use, which is in this case we'll just do it in 2D, and you can do this with the section ALE 2D and changing the Alform to 11. That's a very commonly used element formulation for a 2D analysis. In terms of the basic setup, this is basically exactly the same as mechanical. You want to make sure your 2D plane is your XY plane for plane strain elements, right? For the axisymmetric elements, you want to make sure that none of the coordinates of the nodes have a z coordinate system, and the axis of rotation is always going to be your y-axis. So if you follow that and you set the element analysis up to 2D and the geometry, you would turn the Dyna problem also as a 2D problem. And what that will actually do is I will actually automatically write out, like as I demonstrated here, if you were to change the behavior here, you will actually write out the correct element formulations in the background, and that's a very convenient thing to have for Dyna. Very similar to mechanical, really. On the Dyna side, right, we can also, obviously, I always use LS prep post to post process. So one good thing to remember is that instead of looking at the results, like it's a 3D element, you can actually change the coordinate system to only along the XY plane. You can also do a reflecting of a for example, a axis of rotation, which allow you to visualize a 2D a axisymmetric problem as a full 2D plane cross section, right? And what we can also do is to change the coordinate system upon which we're reviewing results and turning a contour plot from a general 3D view to a 2D view that will have the correct stress components being illustrated right here. Now, in terms of the adaptive remeshing, which is really what allows us to accomplish a remeshing capability, is basically through this keyword template. The control adaptive with the adapt type equal to 8 basically gives you the basic structure for remeshing a 2D element. And these are always adaptive remeshing, which means you're basically remeshing the entire grid, is what's happening with an adaptive equal to 8. Now the control adaptive keyword right here, this basically the control adaptive keyword right here basically controls the nature of your remesh adaptivity, like I mentioned earlier. The control remeshing controls the element size requirement in greater detail. The part adaptive failure, this is what allows you to turn a single part and then into two different parts after the split. So if you were to say, for example, use a knife to cut apart two pieces of material, right? The separation of the first part, which only has a part ID of a single part ID into two different parts, require you to use a part adaptive failure. This basically allows you to properly adapt, properly sort of define the split of a single part into two different parts as you're doing the remeshing. The control that step right here, this is the keyword that's going to allow you to sort of define the contact interface forces after each remeshing step. So within adaptive remeshing, what happens is that each time the body is remeshed, you changes your contact, you changes your boundaries, and you also changes your contact force interactions sometimes, right? So by setting this to 1.0, you turn this relaxation factor off. This is really recommended by the documentation, unless you really have a reason to use it, such as you're seeing some kind of instability, right? So setting this to 1 will be a default within my keyword template, but this is what's needed to control the interface forces. There are also other things like contact and also things like a boundary that you also need to pay attention to. Usually for contact, you want to use body scoping so that you can get the correct remeshing behavior, contact behavior after remeshing. For the boundary, you want to avoid sort of just merging nodes, right? You sort of need to make sure you have the correct boundary defined, and these are the things that you want to sort of pay attention to for adaptive remeshing. But this keyword right here, part adaptive failure plus the control adaptive, right here is the two keyword that's required to be able to generate essentially a piercing analysis, which is essentially a separation of a single part into two different parts through a penetrator, which I will demonstrate in a second. One of the most important thing for a 2D element remeshing is that the adapto is your characteristic element, right? So for example, if your adapto is the same as your default element, so this is my default element, if I were to run an analysis, you see how the mesh isn't changing even though it's remeshing, right? You can sort of see it's sort of remeshing. That's when the adapto and the default element size is exactly the same size. Now in this case, when the adapto is smaller than the default mesh size, what you see is that the mesh will auto update into something much denser through the first remeshing step, right? So basically your characteristic element is going to be the thing that drives the element count. It also forces all the remeshing to be around the same characteristic element size. The max level here tell you how much essentially the level of refinement you can have on your element size. So this also sets a sort of a upper limit to the refinement. You can also use the control remesh to control the element to the remeshing behavior. I think a lot of the correct remeshing response really requires some trial and error in my opinion, right? But knowing the right element size to capture the piercing behavior is the biggest thing I learned from doing this example, right? Is that we want to write the element size to be able to capture the piercing behavior correctly. And what you sort of get as a second example, I'm going to do a demo right after this, right? If you look at the demo here, you can sort of see, right, as I advance the video, right? You start seeing some remeshing. You start seeing some remeshing right there. Oh, let me set it up from the beginning. It's kind of hard to see. 1 second. Alright, so if I were to do this, you can see the remeshing is happening along the way, right? You can sort of see how the remeshing is happening along the way, right? But as you pierce more and more into it, you also remesh as you cut into the material. Instead of stretch the element as you're cutting into it, you just remesh that interface to generate more elements until you fully detaches from the two parts, right? And that is where you have the correct you have the behavior that's intended for separating a single body into two different bodies by through nothing but remeshing along the cut interface. Okay, and that's the first example I'm going to demonstrate. Okay, so the example we have is very simple. So basically all we have is I'm actually going to delete these two parts. We don't really need them. Right, what we have is essentially a single body right here. I'm going to call this the target. I'm going to assign an aluminum material to it. Now, just so we know what the aluminum materials are, the aluminum material is basically MAT24 in Dyna. Basically, I have aluminum material with this characteristic, percent like 70 gigapascal, 0.3% ratio, and I have a multilinear isotropic hardening that I'm adding to the model, and that's going to be my target. And then my penetrator is going to be a steel part. I'm going to use this steel material here to penetrate through it. Okay. All right. Now, in terms of the behavior, I want to set just to plane stress, plane strain. because I want these to be essentially a plane string problem, assuming this thing like it goes infinitely extended into the z-axis, right? You're just cutting this piece of material in half through the penetrators. Okay, with the plane string model, what I can do here is to quickly mesh this. So what I can do here is use a 0.25 mesh. And then I have about 8,000 elements. You can see this is relatively dense already, right? And I have my penetrator and I have my target, both at 0.25. What we wanted to do here is to design either a body-to-body interface contact, right? Which means I can create an interface contact and assign both body to it, like frictional contact assign both body to it, or I can basically select these two parts, assign it to a body interaction, and then change this to frictional and change the coefficient 0.2. What this does is that it turns this into a single surface contact. So if I show you the, well, I'll show you that in a second when I show you the full input file. But basically, this turns into a single surface contact, a single surface 2D contact, automatic contact, which is going to basically allow the penetrator to see the grid. And the reason we use a single surface contact is because as you refine the mesh in this body, right, the contact will change if you only use a regular automatic contact. If you use a single surface contact, you can keep the contact while the mesh is being regenerated, and that's why we're using an automatic single surface contact. All right, on the model side, what we wanted to do here is let's go ahead and set a termination time to 0.03 seconds. That's how long I'm gonna define the problem. I'm gonna change this to 0 and change the mass scaling to 1 into -8. This is about the scale of the problem that you can sort of get a sense of what's going on, right? As I always do, I'm gonna change my default control card to be none. I'm gonna change my default database card to be omit, right? So I want to write my own database and the control cards. The first thing we wanted to do is to make sure we generate a displacement boundary condition at the top of the node, right? And we want to make sure this is gonna be free in the gonna be 0 in the x-axis, and it's gonna be -30 in the y-axis. So what we wanted to do here is to display this thing by -30 millimeter down here, and this dimension right here is approximately 5 millimeters. So I'm displaying a lot to allow me to bend this piece and also penetrating it. Right. Now the second thing I want to do is to be able to apply a fixed support on both ends to keep this part from moving, right? And that's what it's going to bend the center and it's going to penetrate it after I generate analysis. Next thing I wanted to do is to define the section. Now the key thing here to remember that this section object right here is not going to tell you you're not going to be able to change the element formulations, but what you can change is the number of an integration point to 4. This gives you a fully integrated 2D plane string element, and that's the one thing we have to do to be able to correctly define a nip equal to 4 in the section shell card. So as I demonstrated in the presentation here, I don't know if you guys saw it earlier, right? I think I have it listed in here. Yeah. So by changing here, you can change the nip value in your section shell, which changes your number of integration points. And if you change that to 4, you have a fully integrated 2D element, right? Because you have 4 nodes. And that's the biggest thing to sort of pay attention to. Like I said, this thing right here, you can't really change it. It doesn't give you any option. By changing here to plane string, you automatically change the section of this part and this part to 13, alpha 13, which is what you're looking for. All right, and next, what we wanted to do here is let's go ahead and add a control adaptive card. All right, the control adaptive card. I can use my default template here. So if I show you my template, control adaptive 8 right here. Well, let's do it this way. What I wanted to do, let's use my template instead. I'm gonna show you my template real quick. Control adaptive remeshing, adaptive right here. So let me explain this real quick. Okay, so this control adaptive card is my keyword template, right? But basically, if you look at when the adaptive equal to 8 right here, right? These are the things in which you can essentially control, right? So adapt type equal to, so basically when you look at control adaptive, if your adaptive type is equal to -8, right? and that's what essentially allows you to basically use a different layer format. So if this is the format that you're using, if you have adaptive tab equal to 8, and your adapt frequency and adapt toe is gonna be defined by here. Yeah, maybe let's go a little bit easier. I'm just gonna use the default card that I have. Let's use the control adaptive 8. Okay, so we can just use this card right here. This might be an easier thing to understand, right? What we do here is that in the keyword template, what I wanted to actually use is to use a frequency of 3 to negative 4, which means over 3 to negative 2 seconds, every 100th, every point, over 100, it's gonna rematch it 100 different times, which is because my adapt frequency is gonna be 3 to negative 4, and my total duration is 3 to negative 2. So every 0.0001 second, I'm gonna try to rematch every 3 to negative 4 seconds, I'm gonna try to rematch the body. I'm gonna rematch it 100 different times. My characteristic element is going to be 0.25 millimeter, which is exactly the element size of my default element, which means I don't plan to make the element core more dense as I do the remeshing, right? With an adapt equal to 8, it's going to be assigned to mostly a plane strain or an axisymmetric 2D elements, which is what we're refining, right? And that's also give you an R adaptive remeshing. So if you look at the documentation, for example, it's very useful to look at if you look at control adaptive. Right, it tells you basically what happens if you go to AD type equal to 8, right? This is your frequency, this is your character element size, and this is going to be your adapt type of equal to 8, which is your 2D R adaptive remeshing, which is essentially remeshing a 2D element. Completely new mesh is being generated every single time, which is what we want to control. The max level is a max number refinement. We're using 3 to give you some additional freedom for refining the elements, but not by a whole lot. Right, and that's our control adaptive. And the next keyword is going to be the way we are separating on the body, right? So let's use the control. Let's use the part adaptive failure. Right, the part adaptive failure is going to be the keyword that's going to be basically treating part number 1. Part number 1 is going to be my target. I want my part number 1 to be able to be split in 2, which is essentially what this card says. Okay, and lastly, I'm gonna add a placeholder, which is for the control adapt step. This is basically saying we're not generating relaxation factor for the contact interfacial forces between the punch and the target. Each time we're remeshing the target. So as the other target element remeshes, we're not refining the interfacial forces between the punch and the target, allowing essentially just a zero adjustment in that interface. We can also make this number less than 1, which is going to turn on some kind of relaxation factors, which we can essentially use. So if you look at the documentation for control adapt step, right, you can get an idea about the relaxation factor for the contact forces that can be essentially added. You can go to 0.1 for a default value if you believe there's a good reason. The documentation does say that it's highly recommended that you don't do this unless you do see some instability in the contact interface because of the remeshing that's happening. But in this case, because I'm not reducing the mesh count, or I'm not making the mesh more dense on the target or the contact side, I'm maintaining the mesh. I think this option is likely gonna be okay. All right, the last object that I'm gonna add in is a database keyword. This database keyword is my standard database template. So if you look at my template database. Database right here, and I just copy this whole thing over. And what I wanted to do here is to change my time from from 3 negative 4 to 1 negative 5. I think that's approximately right. Yeah, we can make this a little bit denser, a little bit more strict. So 1 negative 4, 1 negative 5, and then that's gonna basically define a bunch of database cards that can potentially be written out, but the most important one is going to be my D3 plot, which give me that additional value. Okay, now that's a basic model setup. So I have my target as aluminum, my punch or my piercer is going to be a steel part. and then I have a displacement driven down over 30 milliseconds, right? I'm going to fix on both ends of the target, and I'm gonna penetrate it, and I'm gonna use control adaptive to remesh the target, and I'm gonna use this card to generate a separate path ID as the penetration occur, which allow you to basically penetrate it through remeshing by itself, right? And once you do that, what you can do is go ahead and write out this keyword file. And then what I'm gonna do here is that I'm gonna go to my Dyna staging. I'm gonna do a demo. Okay, one thing to notice about the demo file is that if you go inside here, one thing that you have to make sure you change is this adopt option, right, inside the part ID, because we have to remesh this target, right? We have to make sure we turn this on equal to 2. So if you look at the documentations, right, if you go to part and look at the documentations, right, and you look at the adopt option, right? This is why we're turning this into 2, because we're doing adaptive remeshing of 2D solids, right? So because we're looking at a 2D element, we have to use adopt equal to 2 to turn on our adaptive meshing of 2D solids, which is what we're doing here. Now, if you don't turn this on, this body is never going to remesh despite all the remeshing that we're introducing here, right? So once you have this, you can basically solve it inside LSDYNA. For example, if I go here and then I just go ahead and do 2D plane piercing. Actually, no, I'm gonna do demo. It should run. And then what you sort of see as a result of this run looks something like this, right? So what you can what I'm doing here is I'm probing the plastic strain over some really high number, and then I can sort of play this at a lower speed. So you can see this thing is gonna penetrate it. Each time you penetrate it, it's gonna generate a new mesh. Right, I'm gonna let it. Now it's gonna start piercing. You know, deform the part first and then pierce it. So each time I pierce, you see more elements being generated as you pierce. You see element gets split, element gets split, element gets split as it generates more element. This is how it's basically doing this kind of piercing analysis. And eventually it's gonna separate both parts into 2 different parts. And the remeshing basically clean up the boundaries of your problem, giving a pretty clean penetration analysis as you're doing this. And that's really the way in which we can basically generate a cutting motion. It's almost like a cutting motion, even though in this case it's like a penetration motion. A 2D element is cheap to run, which is why I did it in 2D. You can also obviously do this in 3D as well. As long as remeshing is allowed, you're able to basically do this kind of piercing analysis. Okay, this is part 1 of the video. I'm going to do a part 2 of the video for more standard self-piercing rivet. This is a dynamo example, which I really liked. I'm going to try to replicate this example as well. Okay, see you next time.